for this topic for factorial design. Like this. This is the common attribute for the experimental design for the factorial design. That we analyze NOVA analysis is also two factors. If you apply the factorial design, you can analyze with more than two factors, maybe 3 factors, 4 factors, and also we have like 2 levels, more than 2 levels for that case. Like for factorial design, we consider the factor that affect, and also within each factor, you can consider the left case for that case. And the same technique that we use the ANOVA analysis to analyze for the case for the factorial design. Right? Okay, if we look at this, for example, okay, for this case, we have 2 factors. We have factor A and factor B, and only 2 levels. Each factor we have 2 levels, high and low level, high and low level. And also we have some response. We have some response for this, and then we have the response is at as high level of B but low level A, like the response is 30, for example. High level A, high level B response is 52. Like for high level A but low level B is 40. This is for also we represent plus and minus, like plus means high, minus means low. And also we can calculate the effect. We usually study the factor of A and B. And also we have the interaction between A and B for A, B treatment. But for that case, if we plot each factor, if it cross, that means we have the interaction effect for that case. That means if you model in the equation, it means y equal to beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 1 to x1 x2. For this case, we have some interaction in the model. And also you can calculate the treatment, like for example, at high A, that's like high A 40 and 52, right, is high A. And minus low A, 20, you get about 20, you get positive. What does it mean? You get positive, that means you increase A from low to high level. Response also increase. That's like if you calculate this. Like for factor B also, high factor B, 30 and 52 divided by 2 minus low B, you get positive also. That means when you increase from low to high, response increase, or you decrease from high to low, response also decrease. For this is the meaning of this. Right? And also if we calculate for interaction, we calculate at low level B, like low level B and high level B, A, that's why the interaction we get 1, for example. If you compare, this is 1, right? And effect B is 11, effect A is 20. For this case, can approximately main effect A and B is high compared to interaction. But sometimes when you model, there is no x1, x2, for example. It's only main effect. You can click by this for another example. If we change some response, we get the interaction is minus. Minus is also high effect because it's 29. If any minus or plus, it's also effect. As I for minus, that means you increase, response decrease. As you decrease level, response increase. But for positive, you increase level, response increase. Decrease level, response decrease. For that case, the meaning of negative and positive for that. If, for example, if we have no interaction, because there is no cost, the left-hand side is no interaction, only A and B. But for left-hand side, we have some interaction. We have factor A, factor B, and also interaction between A and B. When you model, maybe like we have some x1, x2 in the model for this. Like I talk to you, for this case, we can model in the equation that y equal to beta 0 plus beta 1 x1, beta 2 x2, beta 1 2 x1 x2. Right? And also from the data, we can approximate beta 1, beta 1 from average of A, you calculate A factor divided by 2, you get beta 1. Beta 2 is B divided by 2. Right? And also beta 1, 2 is AB divided by 2. For this. This is an approximate technique to calculate beta 1 and beta 2. And also how about beta 0? Beta 0 you can approximate by the overall average of response. Right? This is come from overall average of response. Okay. And then you can represent in terms of the model for this. And also you thought if because beta 1, 2 is very slow, right? Compared to 10.5, 5.5, beta 1, 2 is 0.5. That the top one is quite low, right? You can cancel. That's why its value effect is also main effect A and B. And then you can cancel, but you can only x1 and x2. Right? And then you plot the three-dimensional curve, you get the the pan is not curved, but it gets because it's linear. It is not linear, it's really curved, like for surface or something like this. And this is the control plot. You plot x1 and x2, the line means the constant response at that 122, 25, 28, 31, for example. This is the constant. It's also linear, not curved. Right? Because we represent in terms of this. Right? If you represent in terms of x1, x2, we found that it's curved, not linear. That's right. Because it is a non-linear equation. Non-linear in terms of x1, x2. Right? And also when you plot contour, it's also curved, not linear. The line is not straight. Right? You can call it as a curved line. Right? But it is represent. And we talk to it in the response circuit maturity. Okay, for that technique. Right? For this. Okay. And this is more one factor is experiment. But usually we talk about the two factors. This is better to design this experiment. Okay, for general, we have general factor design for that. If all factor is equal are fixed, but it can easily fixed, you can apply for fixed effect model or level effect model. And also the technique, we use the same technique like ANOVA analysis. At the top level ANOVA, we will only two factors. Right? But for this case, we can apply for 2, for 3, for 4, like many factors. We can do that by factor design. Right? But the technique is the same. You analyze the ANOVA analysis, the same technique. And also the model. This is the average mean for total mean. This is for factor 1, factor 2, factor 3, factor 1, factor I, factor J, factor K, for example. And also interaction between I, J, between I, K, between J, K, and I, J, K. That's right. For these three factors, the main three factors, and two interaction 3, and one interaction of 3, and also some add. We need to say that the topic is ANOVA. And then you construct the table of ANOVA analysis. We have the A, B, C, right? Factor A, factor C, A, B, A, C, B, C, A, B, C, the same, right? And also we have some square, degree of freedom means square, and then we decide by F0 or P value. That if P value less than alpha, you reject. That means you reject effect of A, effect of B, of X3, right? Or you check the F critical for this. And also this is some equation how to calculate SST, SSE for like this equation. It's a lot of equations. That is also the program can help you. But by this equation, we have two techniques by this line or by this line. You can apply to calculate some square. If we look at this example, the soft drink bottle problem, we would like to fill the soft drink into bottle. You have to control the level of volume of the soft drink. Every bottle the same volume. But sometimes it may be added, it may be higher than level, lower than the standard level, right, for this case. The soft drink is often more uniform fuel kind. It should be uniform in the bottle produced by manufacturing process. We have the machine for fuel that for fuel volume is bottle. Okay. And there are three variables that affect the level or the height of fueling. Like for this case, this includes percent carbonation. Because the soft drink we add carbon dioxide, add carbon dioxide. For that case, we call it percent carbonation. And also the pressure for fuel, and the last one, the light speed. Light speed means number of bottle that we fill per minute, per time, or something like this. That's the light speed. This is also affect the level or the height of the liquid, salt, water, or soft drink in the bottle. For this case. But for this case, the pressure and speed are easy to control, but percent carbonation is more difficult to control during the process. Like that. It varies with the temperature. Okay, for this case, the engineer can control carbonation at 3 levels. We choose 3 levels, like 10, 12, and 14% of carbonation. Have 3 levels for carbonation and 2 levels of pressure. We consider 25 and 30 psi, and 2 levels of light speed, 200 and 250. BPM means bottle per minute. That's like number of bottle per minute. We have 2 light speed, 200 bottle per minute and 250 bottle per minute. Okay, for this case, the engineer decided to run 2 replicators for each condition. 2 replicators for each condition, we have 3 factors. 2 replicators, total is 3 factors. Total is 24. Right? Okay, for this we have 24 in random. For that case, the response is the response for this case is deviation from the target field, not the height of the field. The deviation, for example, the height is maybe 1 centimeter or 10 centimeter. The response is the deviation from 10 centimeter. It's maybe minus 0.1, it's maybe plus 0.1, it's maybe 1, it's maybe 2, it's maybe minus or because it's error. Minus that means lower than standard, plus that means over the standard. This is again the response is the deviation from the standard or the spec. Okay. Now for this is the data. We have the percent combination in this 10, 12, and 14. And we have 2 pressure and 2 light speed. Like for example, at 10% combination, 25 psi, 200 light speed, we have 2 replicators. The response is -3 and -1. Right? -3 and -1. -4 means total of each condition. Okay, for this case, the data that we obtain 3 parameters. That's 3 parameters. Okay, and then we calculate by manual for this. We apply for this. Okay, we did not talk about the manual about for this file. A lot of it's not complex, but a lot of you calculate. I suggest you to use the program. And then you calculate for some square error of all this, and then you summarize the ANOVA table. For this case, we test based on alpha is 0.05, 0.05. And then you calculate sum square. You can find that sum square of A, of B, of C quite higher than the interaction. Like from the sum square, I think we can approximately indicate that the main effect is important, but the interaction is not important. And also we can find that the P value, only the main effect is important, but the interaction is higher than alpha. For this case, we can conclude that the percent carbon pressure and light speed effect when you model affect the height of the fueling volume of the liquid aside. For that case, but interaction no. because it's higher than alpha. And also we can plot average filling deviation and percent combination pressure and line speed. You can find that percent combination is high effect. Why is high effect? The percent combination is strongly increased the deviation when you compare to line speed and pressure. The slope is lower than this line. For this is the percent combination is quite difficult to control as we talk the engineering talk for that. Okay, if we use the Minitab, okay, I will show you. And for this step, there is no this in Excel, right? For the Factorial design, it's also in Minitab. And also we have a lot of program, right? SPSS program, a lot of program in the market. You can choose that one. Okay, for this step, we will show you the okay. For this step, we will go to start, right? We show you basic application ANOVA already. For the next is the DOE. DOE means design of experiment. It design of experiment. But for this case, we should factorial design. And the first step we have to create factorial design first. Okay, for this case, we have a lot of choice. Like it's maybe two level. At two level, we will talk to you for the next topic. Like this is a special case, we can use the two level and then we can modify at the same time. Modify at the axis. It's maybe increase from 2 to 3 to 5, but you still annihilate on 2 levels. But for this case, we will show you the general full factorial. Okay, general full factorial. Okay. For this example, we have 3 factors. Right? For this case, the maximum is 15. Right? If you should talk for him, the maximum is also 15. It's about 47, but this program is only 15. Okay. We check this. Okay, 47, right? Yes, but if you can align up to 47, it's not possible. Okay, for this case, we use the general full factorial design with 3 levels. With 3 levels. And then you click design. Right? You click design and then if maybe you can type the name percent combination like pressure or light speed and level. For this case, we have 3 levels of percent combination as A and 2 levels of pressure and 2 levels of light speed. That's right. The number of the gate we have 2 level gate for each. That's right. We have 2 level gate for each. We have drop or not drop. No drop. Okay. And then go to the factor. You can add some information on each factor. Like for this case, we can check the name by factor A. The name is percent power, for example. Percent C. Okay, percent C. And B is the pressure, right? C is the light speed and the speed. Okay. All of this is the numeric. That's why we can the numeric or text. The variable is numeric. We have 3 levels. You can have 1, 2, 3, or for this case, the level is 10, right? 10, 12, 14, you can type directly. And pressure is 25 and 30, for example. And light speed, we have 200 and 250. But if we have to give information for each factor for this. Okay, and then you click option. Right. We have the for this the store design in worksheet. For that we click the result, right? For result, we will show summary result in table, right? And also summary table and design table. For this cycle, we show you some cycle. For this thing like this. And this, okay, and then you click OK. Okay, this is the after you click OK, it will design for you. If we have order, run order, don't worry about that. We have control percent carbon, pressure, and speed. We have percent carbon 10. This is the pressure 25. Response, this is the speed 250. And response, this is the response we have to time. But for this case, we have in Excel. We can call in Excel. Right. This is 10%, 25, 200, 10%, 25, 250, not different one. Oh, okay. And you got this. This is not response. This is speed. I forgot to upload. Okay. The response. Okay. This is the response. Again, this is response based on the deviation from the standard or the spec for that. Okay. You add the response already. And then you go to analyze the factorial design. Go to the spec and DOE factorial design. Previously, only the create factorial design can work. That's why if you start from the first step. But now you have the data already. You can analyze, you can define, you can select option. For this case, you can analyze. Okay, and then you click analyze. You see the response, you click response. Okay, what you like to do, you click response term of this. We would like to see all of this time. Percent carbon, pressure, speed, interaction A, B, AC, BC, A, BC. Okay, we would like to check all of this, include in the model. Like that. Okay, option. We have the weight. No weight. We have 95% confidence when we compare two sides, the minimum and maximum. Okay. And then we would like to plot the curve. This is for the step y at the top. You have many techniques for solve the equation step y for you get to not it up to you for that. And then for the graph, we would like to plot graph or not. Okay, for this case, we would like to plot 4-in-1 the residual analysis. Okay. You can show all of this is a lot of data. You can summarize model for that. And also we would like to show you the design as well. And also you check the fit. You can show for all. Yeah. And also we show the residual analysis is no problem for this. Okay, the accuracy is not. And this is summarize your model. We show you the ANOVA table. Okay, it is summarize your model. We have 3 factors, like relative to. We have number element is 24. Only one wrong. Level 3 to 2. For this percent C, 3 level pressure, 2 level speed, 2 level control, and also this show you the analysis of it. You can find that the linear mean we find is only main factor. Two-way interaction is non-linear term, 3-way interaction. Okay, if we check the linear percent carbon, pressure, speed, you can find that the p-value is lower than alpha. That means we have the effect of carbon, pressure, and speed. If you check the two-way total is greater than alpha. For each C pressure, C speed, pressure speed also is greater than alpha. You reject. That's means no interaction. That's right. And also three-way interaction is also greater than alpha. No interaction. That's right. This is the model that we can conclude that percent carbon, pressure and speed affect the time of the fueling, and also the deviation. And this is the fifth model. We can model for each term, like in terms of beta zero. This is beta zero, beta one, beta two, beta 1, 2, 1, 3, for example. Right? And then we fit in the equation for all this. Right? But for it, you can cancel. You got this is be fit for all. Right? We fit for all terms. And it's maybe beta 0 plus beta 1 x1 beta 2 x2 beta 3 x3 beta 1 2 x1 x2 beta 1 3 x1 x3 beta 2 3 x2 x3 beta x1 x2 x3 or something like that. Most of it fine. But for this case, you can cancel some term. This is only the linear term based on this. The non-linear term cancel for the is no f. But and also, if you would like to analyze further, for example, you would like to plot the factor, like we would like to plot another equal to stat DOE, and then you can analyze some DOE factor design. Okay, and then we have plot is factorial plot. Okay, you would like to plot some graph. If you would like to plot the main effect cost, we would like to plot the graph. Okay, you would like to plot the main effect cost. You would like to plot the interaction cost. Organization. You just plot the main effect for you. This is plot the main effect percent carbon, pressure, and speed. Right, as the y-axis is the deviation. You can find that percent carbon is the high or strongly affect compared to pressure and speed. Pressure and speed also affect, but the higher is percent carbon. And also, if you check the sum square or effect, the value of percent carbon is higher. The value of percent carbon is higher. If we look at this value, percent carbon is 252, right, for SS, but for pressure is 45, speed is 22. That means percent carbon is higher effect compared to of this. What is? Okay, this is also you can plot like some less. Okay. What is it? That means in conclusion, we can find that the percent carbon and pressure and speed also affect the deviation of the fueling, but percent carbon is the high. Because the assumption of engineer that's correct. Because engineer thought that it's difficult to control percent carbon. Okay, in the case of blocking, we can use the block also. For this case, we have some limit, or we would like to check the operator. We would like to the labor, but everything the same except operator different person. Something that we have block, but each block the same condition. Like we have the blocking, but each block is independent. That means there is no interaction between block. There is no interaction between block. What is? We can find that this is factor 1, factor I, factor J, right? And also interaction, but delta is block. There is no interaction with block. But sometimes we find 3 factors, but block is no interaction. So we analyze only on factor I, factor J, and interaction I, J. No analyze on block because it's separated for block like this. Now you can analyze the block. We did not talk about the critical value or F value or P value because we only analyze the effect of factor A, factor B, interaction of A and B. It's the same that we talked previously. But for this example, like we check the method for improving ability to detect the target on radar. Two factors that considered to be important amount of background noise or ground noise or ground cluster. Right. And today, we talk on the type of filter. We have ground cluster and type of filter. We have two factors that affect. Right. And three level of ground cluster and two type of filter. Right. For this case, we have ground cluster is 3 level and filter type is 2 level. For this case, we fix type factor. Right. And then for this case, we experiment by random selecting assessment combination style factor and filter type. And the intensity of this target is increased until the operator observes. For this case, we check with the operator. That means different operator. And operator is blocked. Operator is blocked. Because the operator is convenient to select an operator and keep him partner as and operator refer in their skill and ability to use the scope. Okay, for this we separate it or independent. We consider operator as blocks. Like block 1, block 2, block 3, operator 1, operator. For this case, we have 4 operators. We have 4 operators. Each operator we have like the same filter type and ground cluster. The same condition, but different operator. We have operator 1, operator 2, operator 3, operator 4. And then we study the effect of filter type 1 and filter type 2. And also the counter ground is low, medium, and high. Low, medium, and high. And the response shown in this. This is the one negative for each condition. For this case, we will analyze the effect of I is maybe ground cluster. J is a filter type, and interaction of ground cluster and filter type, and block and add for this. Right? And this is show you the ANOVA analysis table. Right? ANOVA analysis table. We can find that the ground cluster and filter type also affect, but interaction no effect. Right? No effect because the P value is greater than 0.05. That's clear. Okay, and also we check the sum square of ground cluster and filter type. The filter type is pretty high compared to ground cluster, but both of these effect. But filter type is higher effect compared to the ground cluster. That's why compared to the ground cluster, we can find this from the sum square value. It is very high compared to ground cluster, but also effect. That's why also effect, but filter type is higher effect. But interaction is low. Interaction is low effect. You can cancel or you can include because the P value is slightly equal to 0.05, right? But sometimes you can include the interaction, but you can cancel because the P value is maybe equal to 0.05. But a little bit better than alpha for this. For this case, if you use the Minitab, we will use the same like 3A. And we have some replicate for this. We add the replicate at the block. For this, we convert it block on replicate. That means this is replicate in the block. We have 4 blocks. Okay, for that thing. We use everything for this. And I think another is the same, right? We analyze at the replicate in terms of block. Okay, we go to DoE and factor design. You have to create a factor design for it as well. For this case, we have two factors. We have to choose the two factors. Two factor. We have two factor of ground factor. PC, PC and AFT, right? And with this 3-2 level, and we have four toolbox that we call this is block on the picture for this. And then you add the information for the factor. The factor is 3 level. For this case, the level is in the number is 1, 2, 3. We got the low, medium, and high. Right? Okay, we use the 1 is low, 2 is medium, like high. Yeah, sometimes you can use the text. If you use the text, it should be low, high, medium. For that, if you keep numeric, okay. For you consider it 1 is low, 2 is medium, 3 is high. And also for the filter type, we have 2 types, like type 1 and type 2. You can do that. Or you can use the text. That's up to you. Okay, for this case, we use type 1 and type 2. And we have 4 blocks, 4 operators. For this, the result, we would like to show summary table. Okay, and then we have some design table for this. We have to add a response for that. Okay. For this, we have some Excel. Okay, this is we add the response, and then you design already, and then you click analysis. That's right. Click the DoE, and then factor design, analyze. Right. The response. Okay. Okay. For this case, you can check the term option. Okay, that's right. A B. And the option. Okay. Graph go in one or you get the correct. Now, this is no problem for the technique we use, and this is the result. Okay, this is the factorial design for 2 factors. Factor 1 GC 3 level, FT 2 level. This is the summarize the analysis. You can find that for linear or main factor is less than alpha. That's right. Less than alpha. That is a significant effect. FT or otherwise. But you consider interaction is 0.058. That's right. It's the same. That is taught you in your manual calculation. And also, if we would like to check the factor plot, okay, you can go to DoE and factor plot. What is it? What is a lot of? Okay. Previous example. Many examples have been open for that. This is data for previous one. We have to check. This is the previous one. This is this example. Example. Previous one also. But we have to write this. Previous one. And this is a code for data. I see. This is for this one. Okay, for example, that and get it to be do. Yeah, right. You can plot the factor that is there is no cost, there is no interaction. There is no interaction. The last one is like this is like there is no. Like also in filter type cloud class, there's also effect for the CS. That means from you increase from low to high cloud factor, like there is one increase, but for FT is reduced for this. This is for the general factorial design, and also we have the special case. We have the special case, and we talk to you about 2K factorial design and fractional factorial design. For fractional factorial design, if we design for full or general, there are lots of experiments. But this technique we can reduce experiment from, for example, from 100 to a half is maybe 50. For full form, you do 50, you can reduce from 50 to 25. This is from fractional factorial design. And 2K, you have a two level K factor. That's like two level K factor. But in this case, you can modify from two level into three level at the center. But when you analyze, you write the same thing at 2K factorial. You can add some axial like from the top and bottom. You can find level also for this case. Okay, we show you for the next one. This 2K. Usually we use 2K to screen. Sometimes you use 2K and screen first, and then you can cancel some factor. The first step you check for all factors, and then after you use the 2K and then you screen. Okay, we have pressure, temperature, speed, concentration, but sometimes you use 2 and then you can cancel some factors, right? And then you do only 2 or 3 factors, for example, which is the important or the benefit of the 2K, and you add the screen technique, experimental screen technique, right? This is for 2K. 2K means 2 level K factor. Right? If we have 3 factors, 2 power 3, 2 multiply 2, you get 4, multiply 2, you get 8, only 8 experiments. If you have replicate, you multiply replicate n to K. That's right. N means replicate. This is you can calculate number of experiments based on 2 power K. K is factor. Okay. For this case, the factor are fit and design are complete random for the 2K. And also we use experiment based on normal, that's like normality. You have to check the level is normal. Your technique is accurate for this case. And also there is provided smallest number of lines with K factor that we would like to study. You have to go to study. For this case, we usually use as the factor screening experiment. You can use this technique to screen which factor you have to start, which factor not necessary because this factor no effect. For example, you can use the two case to screen your experiment. But if we have a lot of factors, you can use this technique to screen which factor should be started, which factor should be cancelled, for that. Because there are only two levels for each factor, we can assume the next one is approximately linear. That's right, for that case. Does it show you the technique for two factor? Two factor means 2 power 2, you get only 4 experiments. That's right, only 4 experiments. For this case, if we consider the effect of concentration of reagent and amount of catalyst. That's right. We add the sum catalyst and then the concentration in terms of yield or conversion of chemical process. Right. For this case, we have the Fn concentration be factor A. Right. The factor A is concentration of reagent. Factor B is catalyst. That's right. This is in terms of the amount of catalyst. Right. Okay, we have 2 factors. Concentration, we have 2 levels, 15 and 25%. Concentration of A. Concentration of reagent, 15 and 25%. And also amount of catalyst, we have 2 pounds and 1 pound. Again, catalyst is the chemical substance to accelerate the chemical reaction. The chemical reaction. We have 2 factors, concentration and amount of catalyst. Both of these 2 levels, because we decided on 2 levels. Okay, sometimes we can use low and high. Two levels low and high. Low we represent by negative sign. High we represent by positive sign. Right. For this end, we have factor A is concentration, column 1. Column 2 is factor B is amount of catalyst. Again, for factor 1 minus mean 15%. That's right. Plus mean 25%. For catalyst, minus mean 1 pound, plus mean 2 pounds. Okay. And then based on 2 power 2, you get 4 experiments. For this, you can calculate number of experiments. If you need 2 power 2, you get 4. If you have replicate, you multiply n replicate. If you have 2 replicate for it, you get s experiments. For this. Okay, for this case, we have 4, and then we list possible conditions. That's right. We list the possible condition. We have the 4 possible. The first possible is low A, low B, 15%, 1 pound catalyst. Right. And also high A, low B. That's right, 25% and 1 pound. Right. Minus A, this is 15%. Positive B, this is 2 pounds. Right. This is positive A, 20%, 25%. This is positive B, this is 2 pounds. This is all experiment. But for this case, we represent in 3 replicate. 3 replicate means 4 multiplied 3, you get 12 experiments. This is the response. This is the response. The yield of the chemical reaction. This is the response. Okay, if we represent in terms of this is high B, low A. High B, low A. We represent by B. Lowercase b. Lowercase b. This is high B. Lowercase a and b. This is high A, high B. Lowercase a means high A. This is 1. This means low A, low B. This is the symbol, right? That is mean lowercase a represent treatment combination of A, high, low B. B represent A, low, B high. A, B represent high A, high B. And 1 is represent low A, low B. Right, for this. And also we can calculate the effect effect A, effect B, and effect of AB. Because this is the effect by A equal to 1 divided by 2n. N is number of replicates. Okay, number of replicates. AB minus B plus A minus 1. For that. Okay, we substitute n is 3, right? AB, the total of AB is 90. This is, we have 3 replicates and total is 90. This is AB. RA, A is high, A is 100. Minus B, B is high, B is 60. And minus 1 is low A, low B is 80. And then you get the effect A. And the same, you get the effect B, effect AB. You found A is positive, 8.3T. That means you increase level of A or B. That's why response increase. Or decrease level, response decrease. For this case, it's minus 5. Increase level, reduce response. That's right, reduce response. AB also 1.67. And so you found that AB is lower than A and B. That's right, lower than A and B. You do not check the negative or positive. You do only the number to compare. Is it 1.67? It's less than 2 of this. Maybe you can cancel, but you can accept for this because it's quite low compared to the main effect. Right. And they talk to you the positive, what is the meaning of positive, what is the meaning of negative. They talk to you. Right. For example, A effect, this is the recant because it's positive. That means you increase A from low level to high level. You increase the yield. This is the meaning because it's positive. Right. But for the effect B of catalyst, this is negative. If you increase amount of catalyst, it may be decrease the yield. Right. This is the meaning positive and negative. Like that. And also the interaction effect is appeared to be small relative to both of A and B. Okay. Right, we have some to calculate sum square. Right. How to calculate sum square? You calculate contrast. Like for example, this is I is the positive, right? This is I. 1 is low A, low B, A is high A, low B, B is high B, low A, A is high A, high A. Okay, for A, B, A, B. This is A from this. A and B, because this is 1 is low A, low B. 1, low A, low B. A, high A, low B. B, high B, low A. A, B, high A, high B. How about interaction? Interaction is from the multiplication of A and B. Minus, we get positive, right? Positive minus, we get minus. Minus, plus, we get minus. Plus, we get plus. This is the symbol of AB. This is that means plus, minus, and plus for this. High, low, for example. And then you can calculate the contrast. And contrast, we can calculate sum square A, sum square AB, sum square AC. Like for this case, the sum square is calculated based on contrast divided by 4n. Right? 4n. For this case, the contrast is based on the symbol of this. Just for example, contrast A comes from AB, right? Plus A, minus B and minus 1. This is depend on the design. That's right. How about B? B means AB plus B minus A minus 1. That's right. So this is B. AB plus B plus A minus 1 minus. Right, we get this. And AB plus AB plus 1 minus A minus B. Right. And how about the value AB1 is forms the total of this. Right. This is B, this is AB, this is 1, this is A. This is the total of response, right? Total of response because we have 3 replicates. And then we use this technique to calculate the sum square. That's right, sum square. And also found that sum square of A and B is quite higher compared to sum square AB. You can compare based on factor or you can compare based on sum square, right? And also you conclude in the ANOVA table. For this, you can conclude the A and B is high effect, but no interaction. Right? There's no interaction between this factor. And then for the next step, if you consider the model, right? You model only A and B. For this case, A and B. You can model in terms of cost model. This is x1, this is x2. This is the cost model. We have only one plus and minus one. That's right. Plus and minus one. This is y equal to beta 0 plus beta 1 x1 plus beta 2 x2 plus array. And then we represent x1 and xb by the cost. Concentration minus low concentration plus high concentration average, right? Divided by high minus low divided by 2. This is the code. This code is only 1 and minus 1. 1 and minus 1. This is also x2. Like for example, you calculate x1 concentration minus low and high. This is 15, 25. That's right, 15, 25. 25, 50. You get x1 equal to concentration minus 20 divided by 5. This is x2. And then you calculate y equal to this. This is beta 0. This is beta 1. This is beta 2. Beta 0 is come from average of all data. Beta 1 is also effect divided by 2. Effect A. Beta 2 is effect B divided by 2. For this. This is I show you. And then also you can calculate the ratio. Ratio that means you calculate from the actual data. And then you may not predict data. Right. This is the predict data. This is the predicted data. You substitute the term of x1, x2. What it can be substitute in terms of minus 1 or plus 1. Because we transform to the cost variable already. This is the cost variable. The cost variable. Okay, this is the ratio. Right. Okay, and then you plot the normality and ratio, you can get the no pattern. That's right, no pattern. The normal is equal to limit. You can conclude that the technique is accuracy for that. And also this limit, because it's no here, because it's only beta 0 plus beta 1 x1, beta 2 x2. That's right. There is no interaction. No interaction for this. For this case, as I talked to you already, we have a special case in the Minitab. We should the 2K factorial in the Minitab connect. For this, we go to the DoE and Factorial. And then you create, but for this case, we have to Factorial design. To the Factorial design, by generated. To the Factorial design, generated. For this case, we have two factors, right? We have two factors. And also, if you click this, we have some design. It's like for two level, two factor, the possible experiment is 4. Like it's 4. For this case, we have no center point. For this case, I talk to you, we can add a center point. And also number of replicate. That's fine. We have no replicate, but for this we have 3. And not 2. Not 2. No replicate, right? For this. Have a replicate on 3 replicate, okay, fine. 3 replicate, right? We have 3 replicate. Like 3 multiplied 4 is 12 experiment. Number of block, okay, no block for this. and then you add the factor, the scientific, the reaction concentration RC, for example. We have level, you can use the code -1 or 1. You can use the rule, right? It's 1575, for example. And this is the catalyst, amount of catalyst. We have 1 and 2 parts, 1 and 2 parts. And also we have some options. You will fit the model, right? You would like to do not open not for design and downtime. The result you would like to show some table, product table. For the not table, we got to review factorial design with the summary table. Okay. Because if you would like to summary table, like table we use for factorial design, like for this. We show you the data, right? At the list, and then you have to add the response. Yeah, you have to add the response. This response. Response is a G, right, for this, and then we can analyze that DoE factor design. Analyze the factor design, right? So this is response. And also we would like to check all of A, B, and A, B in the model. We would like to analyze all of this model. If you don't like to analyze, you can skip the out like that. Or you can skip all this like in the model like that. Okay, and then we would like to plot graph or not. That we would like to plot that 4-in-1 like this. The result, what we would like to show for all, we will show you for all, like for the step. Okay. This is the residual part, is no problem for residual part. This is the chart. Okay. We have some A and B. This is some limitation, but only AB is lower than this. Okay, we can just set the AB no interaction. It's like what is from this curve. And you look at the summary table. You need the summary table, right? To get the and cap is less than 0.05. Okay, we have some effect, but no interaction. That's right, but no interaction. This is for 2 levels. And also you can plot the curve for this case. You would like to check the response surface for the curve. You can plot for that. Okay, for example, we show you how to plot the curve. After you analyze, this cap will show you. Previously, this cap do not show you. You have to analyze the factor design first. And also, if you do not create factor design, all of this you cannot do. It's step by step. After you create factor design, okay, you can analyze. After you analyze, you can plot any curve of that. For that. Okay, for this curve, we would like to plot the surface plot. Okay, you would like to plot the surface plot, the response. Okay. Amount of gas in x-axis, catalyst in x-axis, and y-axis is the reaction for that. Okay. We show you the surface cost design. And also, we would like to plot the this is the surface cost. And also, you can plot the contour plot. You check the contour plot. This is catalyst. This is concentration of reactant, and this response, that's like this response, this is control plot. And if you would like to plot the control plot, this surface plot, this control plot. Control plot, that means we plot the control at constant response, as constant response. Like this is the control plot. Like this is this zone. If the response of catalyst yield is less than 20, is less than 20. This is between 20 and 22. This is between 24 and 26. This is RC and CAP. That's like for this. You also can plot like this. Maybe I would like to wait for 10 minutes. There's only two of you in this room, another in the Zoom, right? Okay, wait for 10 minutes.